Hey YouTube! So, I'm going to tell you a little bit more about the cube. I'm going to tell you a bit more about quarks and how they work in the cube and in nature. But first, let's look at our little orbit and get warmed up. You remember we looked at generator move like this, and 63 of those brought us back to the solved cube, showing us some 7-fold symmetries and some 3-fold symmetries. We also had a 5-fold orbit. And we're going to look at a generator now where I bring the left side up, top shift, bottom shift, left side back down. Now I return the top, return the bottom. It's a little bit complicated generator. The cube looks kind of messed up already. How many times do you think I have to repeat that? Well, thousands perhaps? It's kind of hard to tell. Let's try that's 2 times. Now let's do it again. Wow. Okay. Another orbit of length 3. So, back when physicists first worked out how to make a bubble chamber and measure small particles of high energies curving through magnetic fields, they found that there were a lot of different particles. They called this the zoo. They had names basically with Greek letters and suffixes, kaons, lambda, hadrons, and mesons of all shapes and sizes. And some people said, who orders that? One guy named Gelman really figured out that there was some symmetries going on between these nucleons, and he figured it out based on a symmetry group. It turns out that the same symmetry group is here on the cube. And a lot of people think of a quark as a particle. It's not really. It's because you can't have a single quark. But because we have godlike powers over the Rubik's Cube, we can make a single quark. I'm going to do it right now for you. Having a single quark is kind of like having a North Pole and no South Pole. Sort of, as soon as you cut your thing in your magnet or your object, you now have a new South Pole. So you can't really have just the North Pole. So this is a quark. You can see that twist of a single corner. And this is kind of abhorrent to people. This is really kind of a devilish thing to have, because it's you shouldn't be able to do this. You can't do this. It's a trick. Obviously, you saw me do the trick. So let's put that back and see what we can really do with quarks. Turns out that quarks are just pieces of real particles. And you say that each one has a 1/3 or a 2/3 charge. They contribute that much, but they don't really exist on their own. So, yeah, you see, when you do this to a vacuum, people really, the residents of this universe get very upset. It's quite rude, so apologize to them in advance here. Distort their whole view of reality. So, let's make some quark objects. So here's a basic, what they call a hadron. You see that I have now 3 quarks. See, on this side is symmetric. It looks like a vacuum over here, nothing going on. Now we have these 3 disturbances, and they have this symmetry that to return it, I go 1/3 of a turn this way, 1/3 of a turn this way. It's the same direction. They're all the same direction of a twist. They're normal matter, not antimatter. Koinomatter, we could call it, or we call it antimatter. Here they're symmetric, so there's just one or the other. And here we have only one kind. And you also see that there are two on one side. No matter how we look at this, there's two here and one here. Or these two and that one perhaps, or these two and this one. So they're not. One is kind of by itself. And no matter how you view the symmetry, there's two ups and a down, if you will. That's how you get this to be stable. And this is what a proton or a neutron is. Now three quarks like this. I'm gonna continue and make a meson for you. So here we have a nice meson configuration directly opposite. You have two quarks on the cube now. But if you look, this one requires a twist to the left, a counterclockwise to return to the vacuum. This one requires a twist in the clockwise direction to return. So this is a quark and an anti-quark pair, also known as a meson. And these, depending on their configuration, they can hold charge. You can see how they could be. In this case, they're quite symmetric. It looks like we have a chargeless object here. And people who study quantum chromodynamics oftentimes are unaware that there's a real model of the symmetries here. And it's quite powerful. I certainly would recommend anybody who's interested in understanding subnuclear physics to take a look at this. Because you got to learn from somewhere. So you notice that after I move the corners around, I have to do a little fiddling to get these edge pieces in the right place. It turns out that what I'm showing you is also valid on a 2x2 cube. The quark is, of course, just a corner piece. So if you look at a 2x2 cube, something with 8 cubies, which is not coincidence, by the way, it's the eightfold way, SU3 symmetry group. You see that you have the same exact quark geometry. Quark geometry does not depend on these edge pieces. These edge pieces do, however, give us some beautiful sevenfold symmetry. And I seem to be having trouble to return to the solved position here. Give me a moment. And then I'll show you some other cool stuff. Okay, here we go. So I'm put the edges back. And now I have a hadron. And now I just adjust my center edge piece. Okay, so we're going to look at one more orbit, a similar one to the first one from this video. The generator goes up with the left, top, shift, bottom, shift, back with the left, top, shift, bottom, shift. So that's the generator, that's one time. So I'm going to do this several times now. So you can tell the cube's pretty messed up already. Looks like it's going to take a lot to get back, but then again we had a similar generator earlier and N was 3. 2 times, 3 times, 4 times, 5, 6, 7, 8, 9, 10, 11, 12, 13. Actually, I think I lost count. This is interesting. If this were a 2x2, you see, would be solved now. Our corners are all good. I believe that's 20. 1, 2, 3, 4, 5. Corners now shuffled. 6, 7, 8, 9. Actually, this is 30. This is what I was going to show you. So now we have, after 30 repetitions of our generator, we have a quark, 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 counterclockwise to return to vacuum, counterclockwise, counterclockwise, quark, counterclockwise, quark, counterclockwise, quark, counterclockwise. So we have here 2 hadrons, 2 quantum matter hadrons. Here's one, here's one. There's a slight shift. And what this is called a deuteron. This is a proton and a neutron, like the nucleus of a deuterium atom. And you can see, and part of the trouble explaining a deuterium atom is what holds the neutron and the proton together. See, here we have depending on how you look at it, there's 2 downs and an up, 2 ups and a down. Of course, there's other ways to look at this. You could see this as the hadron, the quarks, that could be seen as a hadron here and a hadron here, or a hadron here and a hadron here. And it doesn't really matter. You see, they're just part of the same object. And part of explaining the deuteron is why are a proton and a neutron bound together in a nucleus, and that's where the strong nuclear force was invented. But we can see here on the cube that these things are held together because they're part of a single disturbance of the vacuum, and the disturbance is a spherical harmonic with the symmetry, the SU3 symmetry here of a cube. It's not in a dipole. It's a little higher order than that, and you can see it. This is also called the hexaquark, I suppose. Another way to look at a deuteron. And as you can tell, there's a lot of insight to be had by studying this. Now, to return to our original orbit, you remember it took us 30 to get here. So you can see that in regards to how big is the orbit, it should be 90. N is 90 for that particular orbit. So I hope you learned something about quarks and Rubik's Cubes. Should recommend to you the book Meta-Mathematical Themas by Douglas Hofstadter, where I learned a lot of this stuff. Mostly this idea of the quark on the cube was determined in the 80s by some really bright guys at MIT. And certainly not my creation, but I hope you enjoyed it.